I can't know for sure what you were expecting when you clicked on this video, but there's no way you're ready for this. Put on some pants, buckle up, strap in, and hold on to your hats. I certainly hope you brought your hats. Things are about to get crazy. I realize tensions are high, but miraculously I was able to partially recover from that broken drill bit. I went in behind it with a carbide end mill, managed to get about half the drill out. Not great, but I have 2 thread diameters in there, which should be fine. Depending on the screw or the bolt size, the minimum is usually 1.5 diameters. It's not really linear like that, but close enough for these small sizes. So 2 thread diameters should be fine. Now, while I was whittling away at that drill corpse, my clone built these other 2 parts. I don't have it on video, but nothing really complicated here. This is a nose cap, the same bolt hole pattern, and it goes here. We'll get into the details soon enough. The other part is a motor flange, and it'll be assembled here. This was done on the CNC router, and if you can see the finish in there. I threw in a chamfer too, just to give me a little bit more space for a weld bead. Once assembled, there's a step for the nose of the stepper motor, and the 4 screws that hold it on. Before continuing, let's take a step or 2 back. What I'm building here, that thing you saw mounted on the router at the start of this video, is a machine spindle. Well, sort of. It'd more accurately be called a compromise spindle. A proper machine spindle is one of the more complicated bits of kit you might try to design in a home shop, and even harder to actually build. Big picture, this is the spindle body, and will hold these 2 bearings. The large one is firmly pressed in the front with a spindle cap, helping to take some of those machining loads. There's a smaller bearing that will float in the back. This will be installed further up in the spindle body. Once that's in there, there will be a shaft mounted through those bearings with a chuck on one end, about like that, and the stepper motor on the other. This will be direct drive and rigidly connected. These are just ball bearings, not particularly precision. Your off-the-shelf standard ball bearing. This is single row and this is double row. Now, although these can take some axial load, they're not ideal for machine spindles. Now, unfortunately, a matched set of bearings suitable for a machine spindle would probably cost me more than what it cost me to build my router. So those are out of the question here. However, if we keep in mind what this thing will be doing, that'll be used on a CNC router, the cutting loads I expect there, and the precision a CNC router would offer, well, I'm hoping these will be a good compromise. And if I'm careful with my machining and how I assemble this, well, I won't talk too soon. We'll get this together and then we'll run some tests. There's still a little bit more machining to be done on the spindle housing, but for now I'm going to put this aside. And I'd like to do some work on the actual shaft. Again, this needs to attach to the chuck on this end. You can see that's small. I plan to weld an additional piece onto here and then machine it all as one. Ideally, this would all be turned down from one solid piece of, I don't know, 2.5 or 3 inch stock. Ideally, this would be turned between centers. Unfortunately, I have features on both ends that wouldn't leave those centers in there for very long. I mean, ideally, after machining, this would be hardened and ground, but that's a story for another time. Machine spindle for the CNC router. I'm hoping the collet chuck should be good enough. The part is almost to size. I've stopped a bit to let it cool. It's almost at room temperature, but it was hotter. Working from hot measurements is a rookie mistake you'll want to avoid, as it almost always results in a scrapped part. Most times it might not matter, but if your micrometer's out, you'll want to wait for the part to have cooled down. I mean, especially for precision bearing fits like this, a change in only a few tenths could cause them to fall right off. Now, I've also cut some relief between the two bearing seats. The large bearing goes up here towards the front, and the small bearing is back around there. This lathe cuts a bit of a taper. It's old, has some wear, cuts a taper. It's not much and usually not a problem, but again, for bearing fits, it could make or break this part. Cutting in some clearance results in two areas I can address independently. There's still a taper there, of course, but it's over a shorter distance, and there's some games I can play to tune those in a bit. There's also another groove cut up towards the end. This is a gutter for a thread that I'll need to put onto here. There's a nut that keeps this whole pack together and sort of preloaded. I'm going to wait to do that until I get these bearings in. For me, personally, I've got a much higher chance of screwing up these fits than I do that thread. I'm going to do these first, get those behind me, and move on. I'll bring you back then. All right, I'm so close I can taste it. No, wait, that might be cutting oil. So here's the spindly bit. This is the part that will be driven by the motor. And this is the nut that will pull the bearing pack together. It actually goes on the other way. I still have to drill a couple of holes or mill some flats, some way to drive this nut. Anyway, you might have noticed I didn't have any round stock of the right size, so I chewed the chuck backplate out of some bar stock. In hindsight, I should have just karate chopped it round. Live and learn, I guess. It has a small register and there are 4 mounting holes, 4 threaded holes for the bolts that pull the chuck onto this. Funny thing, I made it to the size recommended by the chuck manufacturer, or I made it to their numbers, but the chuck doesn't seem to want to elegantly pop on. It's really close. I mean, I'm pretty sure my part is round, and as hard as it might be to believe, it almost feels like the register recess in the back of this high-quality chuck is maybe a little oval. And I don't want to ham-fist it on there just yet, but it feels like the screws should be enough to pull it home. It's ready for paint. Watching from home, you might be thinking to yourself, geez, I'm sure those weld beads are nicer than they look on video. But don't worry, they're not. I don't know why, but I thought I'd go for that cast look. It turns out I don't have very good tools for really getting in there to blend everything in. So let's talk about what happened. As you can see, I brazed together finished machined parts, which usually isn't very smart. I mean, weldments are fine, but you'd usually leave the finish machining to the very end, after the part has completely cooled and most likely normalized in a heat treat oven. The heat and the clamping and the general manhandling from welding can induce a lot of distortion in parts. And by can, I mean it usually does. What you'd want to do is weld up roughly machined parts, do all of the welding or fabrication that's involved, then it goes back for finish machining. I've never tried this before, though in theory the brazing should result in less distortion. On top of that, all of my parts are quite beefy. The smallest wall section is probably, I don't know, 3/8 of an inch, 10 millimeters. And worst comes to worst, the way this thing is laid out, I could come in and potentially correct, for example, like an out of round where the bearings fit. Maybe. I'm going to clean this up a little bit more, hit it with some primer, paint it, and then we'll come back and see how the parts fit. I'm not exactly sure what color this is, but I went with something between a battleship gray and like a British suntan. I think that looks pretty sharp if I do say so myself. Let's see if everything fits. Alright, I like how that went in there. I like how that feels. Pro tip, if after press fitting a bearing it still turns, it's a good sign. Probably be smart to Loctite these since I don't have easy access to them after this thing is fully assembled. This spinny bit spent the night in what appears to be a humid freezer. Let's see how this works. That's the first section. All right, that should be it. Now let's hope I can drop the bearing in the back. This is a spacer. That looks about right. I don't really have a good way now to get in there and tighten that nut. I'm going to have to sit down and have a talk with the fellow that designed this thing. That hole you saw me mill on the side of this, by the way, is access to these set screws There's two 180 degrees apart. That's for clamping onto the motor shaft. It's not ideal, but it's a D shaft. It doesn't have a key. It would have probably been smarter to get a motor with a key, so this could just slip in and be retained by its 4 screws. But as it is, this is timed to one of the holes on the 4-jaw chuck. So once the motor's on, I can hopefully align it to the flat on the motor shaft, bring one down and snug it up with the one behind it. Anyway, let me cobble together something that'll let me put some torque on this nut. The 4 original screws that actually came with the chuck, I just threw away. I recommend you do the same. I bought some high quality grade 8 bolts. The hardware they give you with the chucks, I don't know, just doesn't give me the warm fuzzies. I don't know if it's psychological, but they even feel lighter than what a real bolt should feel like. I don't know, maybe they're dried out toothpaste with some black food coloring. The nut on the back, by the way, I just tapped home with a punch and a small hammer. I'm just too excited at this point, have too much momentum to slow down and make another tool. I want to try this thing out. I don't know if you can tell, but we're now on the flip side of my bench. Feels like I'm in someone else's space here. The motor is still wired in and it doesn't reach the normal side. In all the excitement, I neglected to buy the proper fasteners for here. So I'm going to have to make do with what I got. I found some countersunk bolts. They're not perfect, but it's the best I got right now. And here it is, finally mounted to the router table. It's been a couple of days, and of note, I did go out and buy all the right screws, mostly because I also didn't have the screws to bolt this thing down with. In the excitement, I was going to use nails, but then stopped, took a deep breath, and came to my senses. As much as I wanted to try this thing out, there's only one thing I wanted more: for it to not look like my neighbor built it. It's on there nice and solid, though it isn't really trammed in yet, meaning I didn't go to the trouble of squaring it with a table or leveling it. It should be close, but dialing it in is on the to-do list. I'm not going to stand here and make pretend I haven't tried this already. I'm not going to dramatically reenact the struggle blow by blow, but let me walk you through the highlights. First, there is some eccentricity to my spindle. Although eccentricity is in style these days, it's really not a good look for a machine spindle. I'm not exactly 100% sure where it comes from, but I have tooth thou run out. That's not necessarily a problem because I'm running a 4-jaw chuck, so I can dial the work in, but at high speeds that off-centeredness isn't ideal. Best I can tell, there's no end play, nothing wobbles or moves in and out, which is a really good sign. It means I can fix this eccentricity on the router itself. Once I get a bit more confidence with this thing, I'll take the chuck off and recut the back plate. Cut it in position using the router. That should get it running dead true. I also made a tool holder, or maybe a temporary tool holder. As you can see, this holds only one tool. Once I get this figured out, my plan is to make a multi-tool holder, like maybe 3 or 4 fixed tools on one block. I think I can then define fixtures in Mach 4 and cheat my way to an automatic tool changer. Put another way, I could have 4 of these tools hanging off the mill axis Z-plate, and the entire spindle and part can move to different locations. The whole table can move. Instead of changing tools directly, it'd be changing the location of the work, which would coincide with a new tool. Think of it like a parallel universe automatic tool changer. Instead of the work staying still and the tool changing, the tools stay still and the work moves to the tool it needs. If I can fit them, that is. I still have to work all that out. I've been playing with this new toy now for a couple of days, and perhaps it's become evident in the clips you've seen, it's got an issue or two. I mean, it's great, a lot of fun. I'm excited about what this adds to the garage, but there are a couple of issues. First, the bird nesting is out of control. It's a little bit better with the carbide insert that's in there now with respect to the high-speed steel, but the machine needs babysitting. I've tried all the settings I could think of to try to get the chips to break. It's just not happening. For now, I've taken to having the tool retract past the work, which gives me a chance to pull any nests free. Not the smartest move reaching in there while it's running, but so far so good. I started off with a high-speed steel tool. This one. This is the one you saw probably moments ago mounted in the tool post. Vertical and cutting on the top. So the work was spinning this way, and the tool was cutting along the top of the work. When I changed to carbide, that's brazed carbide, I also changed the tool orientation. Now the high-speed steel tool sort of worked, but my router isn't as rigid as I'd hoped, at least not in this orientation. Tool post extension plus the length of the tool resulted in a bit of a diving board. So I switched to a tangential cutting strategy. Here the insert is brazed on the face of the shank, and it's cutting on the back. I actually even tried it with the same piece of high-speed steel, still mounted vertically, about like this, and it cuts here in the back, like at that 3 o'clock position, instead of high noon. Set up like this, tangentially, it shifts most of the cutting loads up in the direction of the ball screw. The machine acts more rigid. If you backed me up into the corner and put a gun to my head, I'd probably say it made things about 55% better. Second, maybe third, I don't remember what number we were up to, this motor doesn't have as much oomph as I hoped it would, so I've had to reduce the cutting load. Again, from the previous motor video, I mentioned this motor was a compromise between holding power and torque at speed. As it turns out, the cutting load is that compromise. I was just hoping for a smidge more power. I'm currently running at about 6 or 8 thou depth of cut, depending how I'm feeling, and a max of 4 or 5 thousandths per revolution feed rate. Any more and I can stall the motor. For a CNC router conversion, I don't think that's all that bad. For a CNC lathe, that'd be pretty terrible. On the bright side, however, I am now running a CNC lathe router conversion at constant surface speed. You may have noticed the spindle speed up or slow down as the diameter changes. Resulting in a constant load and some spectacular surface finishes. I mean, the surface finish could still use a little bit of work, but for a router, I mean, spectacular. I did need some help from Mach support to get that set up properly. Those folks have been great, not to mention they have the patience of a saint. I might seem like a nice guy on the surface, but when I start asking questions, let's just say I might have pushed the limits of free technical support. For now, and for the examples you've been seeing, I've been using the turning wizards in Mach 4 Hobby. Interestingly, these aren't available in the industrial version, only the hobby version. The fact that they include them at all with the base license is just amazing. I'd never used them before, of course, but they're super handy and pretty easy to whip out G-code once you get a feel for them. It has some basic building blocks, like basic lathe operations you might expect, that you could build sequentially one on top of the other to get to a finished part. And each operation has refinements you can make to them, and the potential combinations of all these basic cycles could probably make 90% of your parts, without the need to ever leave Mach for another CAM package. I mean, what I'm doing here is pretty basic, but for the kind of parts I make on my manual lathe, I could do it all here in the Lathe Wizards. Again, you build the part geometry step by step, it accumulates here in this list window, and then you can post right to the controller. Okay, that's a goofy program, but hopefully you get the idea. I just sort of made up numbers and positions there. But you can see now in the graphic display area, it's showing the toolpaths we just programmed in, I guess, 3 steps, in 3 turn cycles. There's a surprising amount of control in there too. You can opt to do just the roughing passes or just the finish passes or tweak small offsets to dial your part sizes in. Now the built-in wizards won't do any sort of strange undercuts, so I couldn't do the super crazy parts I was hoping to demonstrate. For that you'd need another CAM package, like Fusion for example, to generate the code, then bring it back here for cutting. Now I did try that only briefly. Maybe it's for the best since I'm only getting started with this thing, but it turned out to be a can of worms. Getting the settings right for Mach 4 and finding the right post processor and tool orientation and just figuring out how it works in Fusion to get it to talk properly with Mach 4. But it's only a matter of time. I'm sure we'll be digging into the Fusion lathe side of things shortly. For now though, this was a spindle build video and not necessarily a CAM lathe video. Okay, again, I hope you're sitting down. This is reason number 2 I selected this motor. The flip side of the compromise, the holding power. I'd like to use this setup as an indexing head. Now I've bodged together some simple code that will do 3 different contour cuts on 3 of the 4 sides. then the spindle should move away and it should sort of do a little bit of showboating. Although I fully expect to lose that end mill, the experiments must continue. Wow, I completely expected to break an end mill there. I mean, it's nothing complicated, just a profile on 3 sides, but I didn't think that was going to work. When this thing is powered on, let me power it on. It's got just this little bit of wiggle, like any more than that and I have to overpower it. But just on its own, it's got this little bit of wiggle, I don't know, between poles or steps and I don't know what. I figured with a small carbide end mill, that little bit of wiggle would have been enough to snap it. Okay, I think that's it. It's been a long 3.5 days out here in the garage. Now I just need to make some calls to see which of the sisters my wife and the kids relocated to. But as far as our little experiment is concerned, I think I'm off to a good start. I still have some tweaking to do in the actual motor settings. Maybe there's a better set of parameters for this thing to accommodate the split personality I'm asking it to take on. I've certainly got my work cut out for me on the cam side of things. From the little I've seen so far, CNC lathe seems like a totally different world than CNC mill. My end game for this, ideally, and if it's possible, is to implement something of a mill turn system on the router. So currently, to make these parts, I either fire Mach 4 up in lathe mode and I do the turning, or I fire it up in mill mode and, well, do the milling. What I'd like to do is do that all in one setup. So imagine like a toothed timing pulley, for example. It'd be nice to throw some stock in here, turn it to size, then come in and mill the teeth, all in one program. But as always, I'm getting ahead of myself. If you stuck around for all of that, thanks for watching. And next time I think we'll jump into the CNC basics. Hopefully I can convey that this sort of stuff isn't all that complicated if you think you'd like to get into it yourself.